So my name is Matthew. I'm a programmer at JumaWorld. So I write Python by day, and Rust is my newfound love. So I'm always hacking Rust during the night. So there's a link down here. So slides.com/Gathu/PyRusty. So you can, if you want to follow along, the slides are available. So that's the link. So yeah, you can follow along using it. Yeah. Okay, so by a show of hands, how many of us have heard of Rust before? Like anyone with? All right, good. Okay. Yeah. So Rust is it's a systems language that has been designed by Mozilla. It aims to cover the same niche as C and C++. And the main ideas behind Rust is that it should be very fast, so it's comparable to C and C++. It's also safe. So I think for those who are familiar with security, C and C++ have a lot of ways where you can shoot yourself in the leg. So Rust is designed to prevent these mistakes, and thirdly, it's designed from the ground up to support concurrency. Yeah. So my talk is based on these three ideas. I'll be introducing Rust and explain how it achieves speed, safety, and concurrency. So before that, I'll just give a brief history of the Rust project, where it has come from, where it is at the moment, and the future. So Rust began as a pet project. There's a guy called Graydon. He was kind of hacking on this new language, and his idea was to, one, have memory safety. Then he was influenced by functional programming, so Haskell, Lisp, Occam, and he wanted to get those nice ideas from these languages and merge them up to a systems language. So initially, Rust was designed to be purely functional. Even the first compiler was written in OCaml. So then in 2009, Mozilla started sponsoring the project. So it moved from being Graydon's side project to his full-time work at Mozilla. And then the core team started growing up. And if you're familiar with Rust, during this period is when now we have sort of the basis for what is Rust now. So there was rewriting of the compiler. So as I mentioned, the compiler was first in Occam. So during this period, the core team rewrote it. So right now it's written in Rust. Then there was a design of a type system, mainly based on the Haskell type system. Then a lot of the concurrency stuff was also done here. Also, we had work on the ecosystem, so designing build tools, designing third-party library repositories. And then around, I believe it was in July of 2015, we had the 1.0 release of Rust. And since then, the community has grown. So we have a lot of community contributions. So I think as of 2 weeks ago, there are over 1,800 contributors to the compiler itself on GitHub. We have over 10,000 crates. So crates are third-party libraries for Rust. So there's crates.io, which is the community repository. And then we've seen the big areas where Rust is being used. So building operating system, there's one called Redux. There's game engines being designed using Rust. And there's a lot of web framework and web servers that are already using Rust. Yeah. And at the moment, I think we are up to Rust.21, which is the latest release. Then, based on the release, so Rust has 3 releases. There's a 6-week cycle. So we have a beta channel for almost the cutting edge stuff. Then there's a stable channel. This is where you have guarantees, backward compatibilities, and such. And there's a nightly channel, which is, I believe, updated every 2 weeks. Yeah. And then just wondering how Rust code looks like. So, yeah, so this slide, it's basically, let me use the mic. So this slide is showing a comparison of Python code, which is on the first code fragment, and the second one is how you'd write it in Rust. So I think one of the major differences is that Rust has curly braces. This is one that you would have in C. But you'll also note similarities. So, for example, the for loop is very close to what we have in Python, but we use that dot notation for sequences, again borrowed from functional languages. Then even the print statement has the same or similar formatting rules as in Python. So it's not very alien. The syntax is influenced by other languages. Yeah. All right, so I mentioned there are 3 things that Rust mainly cares about. One is speed, then there's safety and concurrency. So moving on, I'll be talking about speed. So Rust is it's super fast. It is as fast as C, again as fast as C++. And even in some benchmarks, Rust is even way faster than those languages. But now, you know, how does it achieve this speed? So one of the ways is there's no garbage collection. So garbage collection is this idea of you have a runtime that monitors your program memory usage, and then when some part of memory isn't used for a long time, it will get freed. So this is a lot of languages with virtual machines use this. So Python has it, JavaScript, and Rust uses another technique. It's called resource acquisition is initialization. It is based on what C++ does. So the compiler is smart enough to know when things are in scope and when they go out of scope, and then it will automatically free your memory. Then also, Rust is based on the LLVM. So out of the box, there is integration to the LLVM. So LLVM is low-level virtual machine. It's a compiling infrastructure designed to compile down to assembly, and a lot of the speed-ups in Rust are because of LLVM. So how to explain how we integrate this? So there is the normal Rust code you write, and then the compiler will compile it to some intermediate representation. Then that representation is passed on to LLVM, which will then now do optimization, and at the end of it you get assembly code. Yeah. Another thing is zero-cost abstractions. So the idea here is you can write a high-level code in Rust compared to what you write in C, but then you will not be penalized for this. And again, this is one of the tricks that Rust borrows from C++. Whatever you do not use, you do not get penalized for. And what you use, you cannot write it any faster. So anything from the Rust is designed to be as fast as it can possibly be. Yeah. Then also, just to show a comparison of what I mean by those zero-cost abstraction. So we have some Python code. So we have a list over there, and we are sorting it. So there are two approaches. So one is where we're using the inbuilt sort function, and the second one is we're using a comparator function. So simply creating a lambda function that will help us sort the list. So if we look at how Rust will, how you do that in Rust. So yeah, so you can see that the Rust code is pretty much close to what you'd write in Python, right? And you're not being penalized. This code will run as fast as it will have if it was written in C, if it was written in C++. So you get this abstraction, be able to write code at a very high level, and again, you're not penalized for it. Just to mention one thing, so where I have code fragments, there is a link down there, a playground link. So that link opens up a Rust environment in the browser in case you're interested to actually run that code and see the output. Yeah. Then another thing Rust has is a minimal runtime. So I mentioned, like in Python, you have to have a sort of a garbage collector running in the background to monitor your code. Since we don't have a GC in Rust, we do not need that. And Rust goes a step forward where you can actually compile your code without the standard library. So for example, you're just interested in the language features and you don't need the standard library, you can omit that, and then it means that there's a very minimal runtime. And another advantage of this is that apart from being fast, it is very easy for us to embed Rust. You can embed it where C is calling it, or even Rust calling C. Because of that, very low overhead. Yeah. Then the last thing, major thing for speed optimization in Rust is, that word is so hard. So generic monomorphization. In simple terms, this is a technique that will allow you to write very general code without being, so remember, Rust is a low-level language. So you have a lot of static typing. You have to define the type of your variables, you define the return type and all that. But Rust allows you, based on a system of traits, to write high-level code where you can actually have type inference and all that. But when it's being compiled, the compiler will know and infer those types, and then the code that is produced will be for the actual types. So this makes that you write high-level code, but the code that is being emitted will be very optimized and be very fast. Yeah. So yay. So any questions so far on the speed? Anybody who's learned something new? Right? Good. Okay. So we move on to the next thing, which is safety. So Rust is designed to be memory safe. So you shouldn't get these errors that are common in C, where you can, example, use a memory after it has been freed. So Rust will prevent such occurrence. So, and this is done at compile time. So if your code is not memory safe, the compiler will not compile it, it will tell you. And how Rust does this, it's basically using a notion called ownership. And this ownership will allow us to, you never have to worry about freeing memory, so it's automatically managed for you. So it's different, like in C you do manual memory management. In Rust, you don't. And also, it will apply to resources. So, for example, if you have a file open, you don't have to close it. Rust knows when it's out of scope and closes it. So, what is this ownership system? So, it's very simple. So, Rust will. So the C philosophy is that the programmer knows what he's doing, and C trusts that the code you write will be safe. Now, the Rust compiler introduces some rules. It says you can write whatever you want, but you'll be constrained by these rules. And now these rules are what ensures that we maintain memory safety. So one of the rules is that for every value in your program or in your code, it must have an owner. And then at any given point, the value is only owned by one entity. So there's this notion of borrowing. So I can create a variable, but it's mine, but I can pass it on, sort of lend it out, and then get it back. But at any time, there are no two owners of a value or a reference. And then since the resources of the object is tied to an owner, if the owner goes out of scope, then automatically the resources will also be freed. So that's how we maintain, we do memory management. Then, so here's an example of code you'll probably write in other languages but won't compile in Rust. So the idea here is we have this function that takes some data and formats it into a string. But, and then it returns a reference to that string. So you can see that ampersand s is a reference to the s string. Now the reason why this won't compile is because after the function is done, since the reference is owned by the function, then if the function goes out of scope, the reference will also go out of scope. So how normally you solve this in Python is that you return the value itself, and in that sense you're giving ownership to somebody else. But as long as you own it, the compiler will complain. Then another way where we prevent, Rust also prevents data races. So if you have mutable data, so by default Rust is immutable, so we use this let mute to declare that the data we want to change it. For example, there I'm declaring a vector, and then so when I say let x, I'm getting a reference to the first element of that vector. And then in the next line, I'm trying to append something to that vector. But since I've already passed that reference to x, and it's a mutable reference, the compiler will complain and say that you cannot again try to mutate the vector. So the idea is, if you're not mutating data, you can share it with as many people as possible. But if the value is being mutated, then it can only be shared to one owner who can be able to mutate it. Yeah. So those are the simple rules that Rust uses for memory management. Again, you can use the link to see that this code will complain, and then you can actually see the errors that the compiler will generate. Then I mentioned the third thing, so concurrency. Now concurrency is a big topic, right? So there is the concurrent execution, where you have code being executed independent of each other, and then there is what we call parallel programming, where you have code being executed at the same time, so like different threads and all that. So Rust supports several ways of doing concurrency, so I'll go over them. So one is the traditional one, where you have threads. So there's support for OS threads. So these are simply where you can spawn a thread, then you'll get one from the operating system, and then now you can do your concurrent stuff under that thread. It's also good to note that Rust in itself, I think if you're familiar with Go and other languages, they've been like where Go supports green threading or having channels. So there are no light threads in Rust. At the moment, there are only OS threads. But this is at the language level. At the library level, you can actually implement the light threads. And there's actually a crate that does that. It's called Miyoko. So this is a snippet of Rust code. So we use the thread module from the standard library. And then how we spawn it, or how we create a new thread, is simply call that spawn interface, and then you pass it a closure. So you can see there's that syntax where you have double pipes. That simply indicates that we are passing on a closure. And the idea is that the function you pass to the thread will be running under that thread. So like in this case, we are spawning a thread, and then we are printing out numbers from 1 to 10. And then on the main thread, we are printing out numbers from 1 to 5. And then lastly, we have that handle.join. So it's again similar to what you have in Python. So the join will make sure that the main thread doesn't quit until the child thread finishes. Yeah. Then just to compare it with Python, so again, now this is using threads in Python. So it's very similar, because in Python you start a thread and then you give it a target, and the target is normally a function. So like in this case, I'm creating a closure and then passing it on to the thread and then starting the thread, and then this other for loop will be running inside the main function, and again we wait for the child thread to finish before the main thread quits. Yeah. Then so that is under threads. So there's another way of doing concurrency, which is message passing. So there are a lot of languages doing this. We have channels in Go. There is, I believe, Akka, the Akka framework in Java does the actor model. And the idea here is that you do communication. Since in concurrency you're trying to, there's always like you're sharing probably memory. So instead of communicating by sharing the memory, you share the memory by passing on messages. So you have one actor sending messages to another one, and then now the other, the receiver acting on it. So how this is done is, in the standard library we have a channel. So there's this, the second line. So we use MPSC, which stands for multiple producer, single consumer. So it's a channel where you can have many messages being sent, but the receiving end is one. So like in this case, in my example, I am spawning a thread, a child thread, and then I am passing on the transmitter side. So once you create a channel, you'll get a tuple back that has the transmitter and the receiving end. So you pass the transmitting end to a thread, and then now I send the value high. And then the main thread has now the receiver down there, where I say let received be Rx, which is our receiving end, and then we print out what we got. So in this case, if you run the code, you should get got high. So in Python, how you do this in Python is where you have two threads communicating, and they have a queue. So the producer thread will write into the queue, and then the consumer thread will read from the queue. So it's not, again, Python doesn't have inbuilt support for channels, but if you're to write something similar to like an actor model in Python, this is one way of doing it. So up there you have the producer. It receives the queue and then puts the message in the queue. And then the consumer will read it from the queue. So doing that get, and then it will print out. So down here is where we are creating the queue, then we are creating the two threads, and we are starting them. So again, if you run this, it should give you the same result as in Rust. Then another way of doing concurrency is by sharing state. So this is where you have multiple threads, and then you have to introduce some sort of a lock, such as a mutex. So this is short for mutual exclusion. So if someone is accessing data, they should have the mutex. So this is mainly to prevent data races. So now how Rust does this is a bit more complex, and the idea is so that we can maintain memory safety. So you can see we have a mutex up there, and then we have this arc. So this is, arc is a reference counting. So we want to be able to have some reference counting on whatever we share. So like in this case, the mutex that is shared across the thread will be the owner of the data we are trying to mutate. So for you to mutate the data, first you must have the mutex, since the mutex will own it. So for example, where we are doing the counter lock and then unwrap. So this is where we are actually acquiring the data we want to change. And then the next line is when we are actually changing it by adding 1. So this, what I'm doing here is simply having threads that will increment a number from 0 to 10. Yeah. Again, this the playground link if you want to see that in action. So yeah, so you can see out of the box, Rust actually handles, almost any paradigm of concurrency, and beyond that, Rust makes it easy for you to write your own, concurrency framework. So it has, and how it does this, it uses traits. So there are two traits that are used. So there's the send and the sync traits. Now, a trait is simply an interface that defines some common behavior. And for these two, we're defining behavior that is common when you're doing concurrency. So for example, the send type will ensure that data can be shared across threads. And then the sync type will actually ensure that data is thread safe. So yeah, using those two, you can actually extend the Rust concurrency further. So yeah, yay, we're done with concurrency. Any questions regarding concurrency?
Yeah, I have one question, but it's generic.
Yeah.
That when you start a thread on your operating system, the thread goes to a separate core, or it will be using the same core.
So when you start on the main thread, you'll have a child thread, which will run parallel with the main thread. So it's not on the same execution context, it will be independent. So that's why we pass that closure, so that whatever it's passed to the thread is owned by the thread, and that's another execution context. So yeah, it's concurrency. It's not like in Python, where because of the GIL, we have to synchronize these threads to make sure that at any given time, only one thread is running. No, but in Rust, we'll have 2 concurrent threads. Yeah. Yeah, so you might be wondering, Rust tackles a niche for C and C++. It has memory safety, but what interests you, if you're still wondering why Rust. So these are some of the things that I've found very useful in Rust. So, and I'll quickly go over them. So one is high-level abstraction. So if you go, and this is true, if you go to Google and Google the fastest way to remove spaces in C, this is the answer you get on Stack Overflow. So if you're to write a C function to remove white space, this is what you get. And then I want to show you how you do it in Rust. So now that is the Rust version. It's actually just a 1 line. So this is one of the key things that I find. It's very easy to pick up, considering you'll have the same speed as C. And then even the syntax is still a high level. Then another thing is type inference. So Rust allows you, where the compiler can infer the type of your data, you do not have to explicitly pass in the type. So like you can see, like on my 3rd line, where I'm creating a new vector by using that vec new, I'm not declaring or annotating any types for it. So I have a comment up there. That comment is now how you do it if you needed to annotate types. But the compiler is smart enough to see that we have an element already of type U8. So this is unsigned 8-bit integer. And when we actually push it to the vector, then automatically the compiler will know that our... Then also it supports some functional aspects. So we have closures, there's iterators built in, and there are traits. So just to look at closure. So again, this is very similar to Python, similar to the example I gave, where we are sorting a list of values, and we are using a sorting function. And in Rust is very similar. In Python, you pass it a function, and again here we're doing the same by passing a closure to the sort by function. And then the second example is the same, but now we are doing a reverse sorting. Yeah. Then on iterators. So an iterator simply represents a stream of data. So this is common in Python if you've used list comprehensions or generator comprehensions, where you have lazy evaluation. So like for that first example, I'm simply creating an iterator of the numbers from 0 to 10. Then I'm reversing it. And this reverse will again give me an iterator. And then I'm passing it on to the filter function. Again, very similar to Python. And then now the filter function takes a closure that does the filtering. For example, in this case, we are interested in getting even numbers. And then now the output will be, so 10, 8, 6, like that, now in reverse order since we reversed it. And then in this other example, I have 2 streams of data. So I have cities and population. And then I'm zipping them together, very similar to what you would do in Python. So you have that zip. So you pass one iterator, and you pass it to the other one. So I'm passing the populations to the city iterator, and then zipping them together, and I'll get similar to like a zipped object, which is almost similar to what you would get in Python, like a dictionary with mappings to the city names and the populations. And again, when I print out, that is what I get. So again, you can click on the playground and actually see that in action. Then I mentioned about traits. And I said traits define shared behavior. So this is almost, if you were to write something close to object-oriented code in Rust, it will be similar to this. So now we have this trait called summarizable, and it's simply, we are saying that if any structure has this behavior, then it should implement a function called summary, and this summary should return a string. So the first there is we are declaring a trait, and then in the second example, we are now implementing it. So I have this structure called tweet, has a username, content, and a retweet, and then I implement the summarizable. So again, it's now defining the summary function, and then now passing in logic. Like here now I'm formatting the username and the content. So now this can be used, so you can have a struct that represents an object or a class, and then you have associated functions for it. Yeah. Then another exciting thing about Rust. So you might be wondering, we are at PyCon, and this is Guy just talking about Rust, which might seem alien to Python, but Python itself is written in C, and sometimes when you probably writing some code that you find slow, you might result in writing a C extension for it, and then now having Python call into that C. Now the good thing is that Rust has a foreign function interface that makes it really easy to call it from other languages. And how you do it is basically how you do it in C. So like, I have an example here. So I'm defining a function in Rust that will multiply the input by 2. And then I have that no mangle. Simply that is a directive to the compiler not to change the names. So there's no name mangling there. And then you use C types in Python to call into this Rust function. And it's the same way that you'd use to call a C code from Python. So Rust will expose a C interface that Python can use. And again, it will still maintain the memory safety, concurrency, and speed. Yeah. So yeah, I like to think Rust is a friend to everyone. And whatever you're extending it, it's very easy using the foreign function interface. Yeah. Okay. So, anybody learning something new again? Awesome. Great. So, just to wrap up, I want to talk about the ecosystem. So this is beyond the language, right? So for example, if you're interested in doing Rust, how do you get up starting a simple library or even a binary? So the first thing is Rust has this tool called Cargo. Cargo is a build tool, and it's also the package manager. It also do tests for you. So how you start a project is you run cargo new. So in this example, we are creating a hello world binary. So we pass that directive --bin to declare it as a binary. And then cargo will create to you, it will create a folder, hello world, and it will have a toml file. So this is a manifest file. And then now you will have your main RS file. So the manifest looks like this. So it declares a package. The name is hello world that we used. And then it also has the author. So this information is picked up from JIT. So automatically Cargo will even initialize JIT on that folder. So there's also an aspect of version control. And then, so the main RS is simply a main function with the hello world. And then once you now hack Rust, do your stuff, again, Rust is a compile language. So how you compile it is just telling Cargo to build, then it will build your code. And then if you want to run the code, you just do Cargo run. And Cargo run will support even passing arguments to your binary. Yeah. So, yeah. Good. So then, how to get started? So, obviously the first thing is to get Rust on your machine, right? So there's this site, rustapp.rs. So if you just go there, you'll get instructions on how to install it. And if you're on a Unix system, you can just do that curl and then that link, and it will automatically install Python for your platform. Then also we have an official Rust book. So it gives you a tutorial. It's a guided way into learning Rust. Yeah. So yeah. So I'm done. So any questions?
Yeah, one question. How other Python libraries, like for image processing and stuff like that?
So at the moment, the ecosystem is still young. There's some areas that are not fully developed. So a lot of the work is mainly on web frameworks. These are then operating systems. But it's always good. I wouldn't say that Rust is production ready, right? But I know some people, if you're doing a lot of web stuff and you probably want to have a faster server or speed up your web framework, there are already mature libraries written in Rust. So I know there's like the Sentry.io, they do error aggregation as part of their stack is using Rust. There's also One Signal, they do push notifications, and they have the entire backend written in Rust. So yeah, for web, if it's web, the ecosystem is mature enough to be used. Yeah. Okay, thank you.